looking at. So our basic design process here is going to start by coming up with our KL over R calculation. We want to check to see whether or not this is considered slender or not. So we're going to do that KL over R and check. So I'm going to start with table 7.1.3 and look at our axial only. So this is here our table 7.1.3. I'm looking at axial only. So I'm looking at PF of 2,500 kilometers. So I'm going to read across here 2,500 kilometers and come across here and say, okay, those are the particular column sizes that work. And we've chosen a 350 by 350. Right, so coming down here and getting a reinforcing ratio of about 2%. 7.1.3.
And do you always try to round up to a full percent, or you do 4.5?
I'm going to recognize that I have moment on here. This is just axial, so I'm going to over-design. I'm going to overestimate.
We're checking the slenderness here, is that what's going on?
2%. Pardon me?
The slenderness, that's the first thing we're doing?
Yeah, so in order to do the slenderness, I need to have a, I need to be able to calculate my my column size, basically. So, also off of our table here for 350 by 350, we get our AG at 0.1225 meters squared, and we're going to calculate our R at about 0.3 H. We're going to use a K value of 0.9. That's that kind of standard configuration that I was showing you before. This one right here. That's your typical connection details, so we're going to use that K of 0.9. Well, this is, do you have a table or something? And 115.2. From there, we'll calculate our KL over R. 0.9 times 3,000 millimeters high, 105, and I get 25.7. This is less than 100. So we're okay so far. Yeah.
Why was that 0.9?
That's this configuration here, this kind of standard configuration of approximately same stiffness between the beams and the columns.
That's pretty normal.
Yep.
What is that other elastic one? What is that supposed to represent?
So this one here, or this one? This is, we have top floor and bottom floor, and then continuing on the floor above and continuing on the floor below.
Okay. So how do we know that dot is treated differently for some reason? Like why not just do another plus sign?
Well, yeah, I'm not sure why they drew it differently here. They got the plus here, but they could have drawn it just there. They put a support at the bottom there. Yeah. I think the reason they did that differently here is to show that the support in this configuration, you're kind of treating it like a pin as opposed to a fixed support.
Do we always use 0.9 in our case?
No, I'll in some cases I'll give you the support conditions. So it's you know, it'll be elastic at the top and stiff at the bottom or something like that. So it's kind of looking up off the table. Right. So we now know KL over R. We know it's less than 100. So so that means we're okay to use our simplified method. So now I'm going to calculate that other side of that equation. I'm going to call this KL over R max. is this value here, 25 minus 10 M1 over M2 divided by, divided by F prime C and AG. Now, first of all, our M1 over M2 is equal to minus 0.5. Right, again, negative because double curvature, and of course M1 was half of M2. And again, this number cannot be less than minus 0.5, so this is equal to minus 0.5, so we're okay. So we can stick that directly into our formula. So as we plug in our values here, I get 25 minus 10 times minus 0.5. Watch the two negative signs in here. And divided by square root of plugging in PF, F prime C, and AG. Now this is kind of a weird set of units. Normally as we're working in units, we work in a compatible set of units. So the most common one that we're using is newtons per millimeter squared is an MPa. So if I do everything in newtons, millimeters, and MPa, I know I don't have to do anything specific. Right? The units all work out. This, what I put in here, is meganewtons divided by MPa and meters squared. Right? So PF I put in meganewtons. F prime C is in MPa, and here I've got MPa. Right? So this works out to 10 to the 6 newtons divided by newtons per millimeter squared times 10 to the 3 millimeters squared. Right, so 10 to the 3 squared is 10 to the 6, and that cancels out here. So I've got newtons canceling out, millimeters squared canceling out. This actually works out. So this is a compatible set of units. Meganewtons, MPa, and meters squared is a compatible set of units. It is not one that is very commonly used, but it works really well for this concrete scenario.
Can we do it just in newtons then?
Absolutely. If you want to convert this and put it in newtons, leave MPa as is, and put in your area in millimeters squared, absolutely, it works out fine. This is just, it's another compatible set of units, one that's not commonly used, but you remember our table for PF that we looked at first was based off of meganewtons. Right, F prime C is based in MPa, and our table that we looked at with meganewtons gave us our area in meters squared. That's why, because this is a compatible set of units.
Our M1 over M2, it's negative because of the double curvature?
Yes. Yeah.
Is that stated in the text?
Yeah.
Should we just throw a negative in front of it?
Yep.
Okay.
Okay, so now we've got some numbers. Again, we know that we've got a compatible set of units working in here. Again, this is going to work out as an entirely dimensionless value. And we calculate this out, and I get 39.25. This is greater than our 25.7 that we calculated over there, so I can neglect slenderness. Okay, so this is our next table that we're going to look at. Right, again, we're working with a 350 by 350 column. So we're in this configuration right here. And remember that the reinforcing that we pulled up off of this table needed to be about 2%, right? Just due to axial alone, right? The moment will require us to use a little bit more. Right, so how much more is dependent upon your kind of the ratio between your moment and your axial. If you've got a lot of moment, not much axial, then I'll need to overestimate quite a bit more here. So what I'm going to do here is I'm going to choose a value going with 6. Oh, hang on, that's the 4 faces. In my example, I'm using the 2 faces.
Does it matter which we use?
Actually, no, it doesn't. When we're looking at a full calculation, we're going to have bending in two directions, right? So you may end up with a situation where one direction governs, but in most cases, you've got, you've got a frame in north-south direction and a frame in an east-west direction. So you're going to have bending in both directions. So in most cases, we're going to actually end up looking at in all four faces. Question, Greg?
Yeah, I was wondering, does this AG change based on your PT percent?
No.
So why do we need PT for?
That's where we're looking at it right now, right? So we know for axial alone, we need a roti of about 2%. That's just axial. So taking into account a bit of bending, we're going to aim for something around the 2.5% range. So let's bring this down a bit here. So we're looking at a 350 by 350 column. Right, so 350 here by 350 here. And I'm going to pull in this configuration right here, 2.45. So we're going to take our 350 column and I'm going to reinforce it with 6 25M bars. So that's 3 on each of 2 principal faces. Right, giving us a reinforcing ratio of 2.45. Right. Any of these other configurations, like this one here, that's close to 2, right, might work for the axial, but it's certainly not going to work when we take into the moment into account. Right, so 2.45 or 2.45, so those are kind of the two choices we're looking at. Maybe that one might work. We could try it. But, so we're going to try here with 6 25M bars. So try 6 25M bars. So we got our 2.45%, better than what we looked at on our first part. So now I'm going to calculate 2 quantities out of here. Our PF over AG, so 2.5 meganewtons divided by our AG, 1.225 meters squared, and this is 20.4 MPa. Right, again, meganewtons per meter squared is an MPa. That's that unit that we were talking about here. And I'm also going to calculate our MF over AGH. Right, so MF, this is our 80 kilonewton meters, divided by 0.35 meters cubed, right, because AG is B times H. Well, for a square column, B and H are the same, so that's H cubed is what we're left with here. So kilonewtons per meter squared is kPa. So then I'm going to take this and multiply by 10 to the minus 3, turn that into MPa. I get 1.87 MPa. Now I need to figure out what my value for gamma is.
So we can assume that MF is equal to M2 because M2 is always larger?
Yeah, it's either M2 or MC. Right, our second example, we'll do the slenderness effect, and we'll have to do that
So
multiplication.
whichever is larger between
Yep.
M2 and MC.
Yeah, which is always M2, yeah.
That H is the width of the column.
Exactly, that's right. So this is B times H times another H. But B and H are equal, so this is H cubed.
Yeah, don't get it confused with height.
Yeah, it's not height, that's why that's the L.
Yeah,
It's height.
direction.
Okay, so we're going to look at this table here now. We've got, now that we know we're looking at a 350 column, there's our 350 row in here. And we know that we're looking at 25 M bars. 25 M bars here, we get a value of 0.64. Sorry, 6.4. Right, these are the 2 points that I want to plot, and this is going to tell me which curve that I want to look at. So now we're going to be looking at, what did we say here? This was 35 MPa concrete, and so I'm going to find a gamma of 0.6. So we want bars on two faces here. We want bars on two faces. There's bars on two faces. 25 MPa, 30, 35 MPa, and a gamma of 0.6. Right, so again, we're looking for, again, rounding down is gamma is conservative. So we're using gamma of 0.6. There's our 35 MPa in here. And we've plotted 2 points here. We've plotted 20.4. Right, so here's 20 right here. So this is 21, 22, 23, 24, 25. So 20.4 is coming out about there. And then our F over AGH is 1.87. And of course, I scroll down just a little too far here. 1.87. Right, so there's a 1.2, 4, 6, 8, 1.87 is coming up around here. Pop that back down again. And I want to find where these two intersect. Come up to the point right here. Now, our reinforcing ratio that we used was 2.45%. So what I have to do is interpolate a curve between the 2% and the 3%. So my interpolated curve is... Oh, that's there's that interpolated curve. And so now we just say that the point is inside the curve, so it works.
Inside is below or above?
Below. Yes?
If you were just starting over, could you then go look at the gamma 0.7 and say that if you interpolate between those two?
Absolutely, yes, yeah. Yeah, so if it's, we know that if our gamma here is actually 0.64, so it's a little bit bigger. And remember what that's going to do is take the nose of this and shift it over. We're here mostly on the axial side, right? This line here is not going to shift over, right? It's the nose that's going to shift over, right? But we're inside, we're close, but it's inside, so it's going to work.
Can you explain again how you tell that it's okay? I'm not really getting that part of the quick.
Right, so
You've drawn your line, I see where it intersects.
yeah, so we got a curve that comes out like this.
Yeah.
Works. Doesn't work.
But which curve are we comparing it to?
The blue one, right? So this is our interpolated curve between 2% and 3%.
Okay.
Right,
So that's the 2.45?
That's our 2.45, that's right. So this is an interpolated curve here at 2.45. Now in this one, I did not need any of the K values, right? Because we're not doing the PC, our Euler buckling load.
And the PT is the ratio, right?
That's right. Yeah, so the PT, the rho T is the slenderness ratio. So we'll look at a second example, which probably won't get all the way through it. But
that is the end of that, right?
That's the end of it. That's right.
Confirm your reinforcing ratio and you're good.
Now, our second example.
Do you have to do spacing for your 10M ties, like your what do you confine this reinforcing?
Yes, so there will be a spacing. I don't have in my notes here where the spacing is. But yes, there is 10M ties. There is a particular spacing in order to confinement. It takes into account locations of where we expect plastic hinges to develop.